So let us start the class, students. The earlier classes we have discussed alpha, beta, gamma decays. In today's class, we are going to discuss the nuclear properties. What does the nucleus contains and what are the properties it has? So, so if you see, I try to share the screen. So, properties of nucleus. I hope it is sharing. Uh, Here, we are going to see what are the properties here. So, I hope you know what does nucleus contains. So the nucleus contains two particles. Okay, one is proton and another one is neutron, isn't it? Hmm. So their masses, proton's mass and neutron's mass, both combine to give the nucleus mass, isn't it? What is the proton mass then? Proton mass is 1.67 into 1.672 into 10 power minus 12, 27 kg. Okay. What is the neutron mass? Mass of the neutron is 1.67492 to 10 power minus 27 kg. So these two constants that gives the mass of the nucleus. Okay. So uh, a proton is positively charged, you know that, and a neutron is neutral. It carries no charge. Okay. So the neutrons carries no charge. The charge of the proton will be 1.6 into 10 power minus 19 coulombs, whereas the mass is 1.672 into 10 power minus 27 kg, and the proton's mass charge is 1.6 into 10 power minus 19 coulomb. Okay. Both proton and neutron, this proton and neutron combined together we will call it as a nucleon. What do you call? We will call it as a nucleon. So we will call it as nucleons. If you see the number of protons, how you will indicate? By Z we will indicate, right? The number of protons are indicated by Z. That is nothing but atomic number. The number of protons and neutrons. If you add the protons and neutrons, we'll call it as a mass number. That is, we will indicate it as indicate by capital A, isn't it? So here if you see, Z means what? Z is nothing but number of protons. Protons number is given by Z. And A is what? Atomic mass. Mass number. That is given by protons plus neutrons. Isn't it? So protons and neutrons we call atomic mass and Z is atomic number. Okay. So these two, proton and neutrons, combinedly call it what we will call? We will call it as a nucleon. Okay. So what we will study? We will study the properties of this nucleus. Means we will try to study the radius uh, and their charges and how the masses will be and what are the interaction between those in the nucleus, the protons and neutrons. We will try to see that. Okay. So first of all, we will try to see the nuclear mass. Let us see. So what is nucleus? Nucleus consists of the elementary particles, that is protons and neutrons. Elementary particles, protons and neutrons, which are known as nucleons. We'll combinedly call it as nucleons. Okay. A proton has positive charge of same magnitude as that of the electron. Okay. So positive charge of the same magnitude as that of the electron. Electron and proton has same magnitude, but they are negative. sign is different because positively charged proton, electron is negatively charged. Okay, and its rest mass is about 1836 times the mass of the electron. So the proton's mass will be how much? The mass of the proton will be 1836 times more than that of the electron. Okay. A neutron is electrically neutral whose mass is almost equal to the mass of the proton. So neutron mass and proton mass are comparatively they are equal. Okay. Here we will indicate these masses by by signs like m suffix p and m suffix n, where m suffix p is mass of a proton and m suffix small n is a mass of a neutron. Okay, you try to understand the things, and also that mass of nucleus will give with um, that is m suffix capital N, that is number of nucleons. Let us see uh, here. If you see the nucleus of an element is represented as this is uh, XZA, that is here it will be like this now. X is element here, A is given here, that is mass number, that is number of protons and neutrons. Z is given here, so Z is given here. So here X is element, A is mass number, and Z is atomic number. Okay, atomic number means number of protons. Mass number means capital A is nothing but protons plus neutrons. Number of protons plus neutrons, number of protons here. Okay, this is X is element. That is so X is a chemical symbol of the element. So chemical symbol of the element is X here. So Z represents the atomic number, which is equal to the number of protons and capital A. So Z represents the atomic numbers. This represents the number of uh, protons. Z represents the atomic number of protons. Okay, and that is and A. Here A will be there, right? The A is what? The mass number, which is equal to the total number of protons and neutrons. This A indicates what? Total number of protons and neutrons. The number of neutrons is represented as capital N, so which is equals to A minus Z. If you subtract this A minus Z, what happens? The mass number minus atomic number. Atomic number is number of protons. Mass number is what? Number of protons plus neutrons, right? Number of protons minus plus neutrons minus number of protons means what? We will get the number of neutrons. So A minus Z indicates that number of neutrons here. Okay, that is represented how? That is represented by capital N. Okay, for example, chlorine nucleus represented as this is the chlorine nucleus. Man, this is represented like this. Cl. Cl. Here 17 is the uh, atomic number actually. So here 35 is the mass number. 35 is mass number. So what does it indicates? It indicates that the 17, these are the number of protons which are present in the nucleus, and number of protons plus neutrons are how many? That is 35. So there are how many neutrons then? We have to subtract this A, that is 35 minus Z, that is 17. If you subtract 35 minus 17, you will get 18, isn't it? So this is capital A, this is capital A minus Z. This is the formula you have used here. So A minus Z means 35 minus 17, which gives 18 neutrons. Okay. So 18 neutrons we have. So then next, if you see, I hope you understood this one. This is that element which is having number of protons and neutrons. Z indicates number of protons and A indicates the number of neutrons. Okay. Here, chlorine is the element which is having 35 nucleons and 17 number of protons. If you subtract nucleons minus protons, you will get the neutrons. So let us see the first property, that is nucleus size. So how the size of the nucleus will be? Let us see. So if you see a chocolate, if you see a pin, how it will be? It's small, right? When you go for the nucleus of that pin, it will be very, 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 very small, isn't it? So it is in a Fermi levels. So this nucleus size, if you see, according to Rutherford's particle, so according to Rutherford uh, particle scattering experiment, the radius of the nucleus will be radius of the nucleus and its mass number A is given by, that is R directly proportional to A power 1 by 3. That is R is equals to R naught A power 1 by 3. R naught is the constant of proportionality and is equals to 1.3 Fermi. Okay, 1 Fermi is equals to 10 power minus 15 meters. So here nuclear diameters can be measured in two ways actually. Two ways, two of which are scattering of fast protons or neutrons and by scattering of high energy electrons. So Rutherford, as a result of his experiments of on alpha particle scattering of a thin metallic foil, so he has concluded a distance of the closest approach, the distance of the approach of the alpha particle to the nucleus of the scatter can be regarded as a measure of size of the nucleus. Okay, so which comes closer, that the distance of the closest approach of the alpha particle to the nucleus of the scatter can be regarded as a measure of size of the nucleus. So which comes closer to the alpha particle, that he has come as the size of the nucleus. He found how he found that this distance will be order of actually 10 power minus 14 meters. He found that the distance will be how much? 10 power minus 14 meters. The radius of the atomic nucleus can be determined by this form actually. So the radius of that atomic nucleus, any nucleus, we will find by using this form. That is R directly proportional to R naught A power 1 by 3. Here R naught is the proportionality constant. Okay. And it has some value actually. What the value is, it is having R naught is having some value which is a constant. This R naught has a value of 1 point as 1.4 into 10 power minus 15 meters. Okay, has 1.4 into, if you want to solve, you can solve the any, if you want to find the size of any nucleus, any element nucleus, you can find by using this formula. The R naught value will be constant one, that is 10 power 1.4 into 10 power minus 15 meters. Okay, that is nothing but 1.3 Fermi, nearly 1.3 Fermi. Okay, so this is the value of the R naught. Next, if you go here, we will see uh, the nucleus density, if you see. So the nuclear density can be calculated from the mass and size of the nucleus. So we need mass and size of the nucleus, because density formula is what? What is density actually? Mass per unit volume, isn't it? We have to know the mass and also size of the nucleus so that we can show the density. We can find the density by hence here the nuclear density can be calculated from mass and size of the nucleus. Okay, that is rho n. That is density of nucleus. Density of nucleus is given by nuclear mass by nuclear volume. Mass by volume. Okay, nuclear mass by nuclear volume. That is given as nuclear mass is equals to that is A into mass of a nucleus. That is mass of a neutron. Okay. So that is nucleus mass is equals to A into Mn. A is a mass number and Mn is what? Mass of one nucleon and is approximately equal to how much? 1.67 into 10 power minus 27 kg. Okay. A is a mass number here and small mn is what? Mass of one nucleon and is approximately how much? 1.67 into 10 power minus 27 kg. It is nearly equals to mass of the proton, isn't it? The nuclear volume, if you see, what is the volume of the nucleus? That is 1 by 3 into pi r cube. Okay, 1 by 3 into pi r cube. So r is the here radius of the nucleus. R is what? Here the radius of the nucleus here. So by this we can find mass of nucleus mass is how much? M capital N, isn't it? M suffix capital N is the mass of the nucleus. And what is the volume of the nucleus? That is 4 by 3 pi r cube. R is the radius of the nucleus, isn't it? So by using these two, mass and volume, we can find the density. That is rho n is equals to mass of the nucleus by volume, mass of the volume. That is M suffix N by 4 by 3 pi r naught cube, isn't it? So the nuclear density is calculated as how much it will be? 1 point. If you substitute the values, mass of the nucleus will be how much? 1.67 into 10 power minus 27. And same, if you find for the volume also, 4 by 3 into pi value is how much? 3.14, isn't it? R naught value is nucleus radius. Just now we have discussed nuclear radius. So you substitute these values and you will get that nuclear density will be 1.18. 1.18 actually, it is 1.8. So okay, 1.816 into 10 power 17. It is 10 power 17. It is suffix. It is exponential term. That is 10 power 17 kg meter cube. Kg per meter cube. That is meter minus cube. Okay. So 10 power 17 kg meter kg by meter cube, because mass by volume, isn't it? Units will be kg per meter. So 1.816 into 10 power 17 kg per meter cube. The high value of the nuclear density shows that the nuclear matter is in an extremely compressed state. Okay. The high value of nuclear density shows the nucleus matter is in extremely compressed state. As the volume of the as the density of the nucleus is more, which means what? The state is heavily dense, isn't it? So it is dense with so many protons and neutrons in a small area. That is what it indicates. The value, as the value increases, the compressed state nuclear matter is compressed heavily. Okay. So nuclear charge, if you see. So here the charge of the nucleus is due to protons presenting. Okay. Each proton has a positive charge equal to 1.6 into 10 power minus 19 coulomb, isn't it? How much? 1.6 into 10 power minus 19 coulomb. So the nuclear charge is equals to Ze, and where Z is the atomic number. The charge of the nucleus is due to the protons present in it. Each proton has positive charge equal to 1.6 into 10 power minus 19 coulombs. The nuclear charge is equals to Ze, where Z is the atomic number. Okay. So let us see the mass here. Mass of the nucleus. The unit of mass is kg here. The unit of mass is kg. One atomic mass unit is considered as the 12th of the mass of the carbon atom. So one atomic mass unit is how much? One atomic mass unit is 1/12 of 1/12 of the mass of the carbon atom. Okay. So carbon is what? Carbon is an element which atomic number is 6 and mass number is 12, isn't it? So here a unit of mass is kg here. One atomic mass unit, 1 AMU we will call it as, is considered as a 12th, 1/12 of carbon mass atom. Okay. Carbon of atomic number 6 and mass number is 12 and has mass equal to 12 AMU, that is atomic mass unit. One atomic mass unit is equals to how much? 1.66 into 10 power minus 27 kg. Remember this one. One atomic mass unit is equals to how much? 1.66 into 10 power minus 27 kg. The mass of a proton. The mass of the proton is how much? MP. Mass of the proton is equals to 1.007276 AMU. So mass of the proton is 1.007276 AMU and the mass of the neutron is nearly equal, isn't it? The mass of the proton and mass of the neutron are nearly equal, that is 1.008665 AM. Okay. So this is about the mass. We will study, we will find the mass of the nucleus in AMUs, that is atomic mass, and it is 1/12 of the mass of the carbon atom. Okay. So next, if you see the energy of the equivalence, uh, the energy of the equivalence can be calculated in electron volt. Einstein mass energy relation, you know that, is E is equals to mc square. Here m is what? M is how much? M is equals to one atomic mass unit, which is equals to 1.66 into 10 power minus 27 kg, isn't it? What is the speed of the light? That is speed. Here c is how much? Here c is how much? C is here 3 into 10 power 8 meter per second. So velocity of speed of light it is. So E is equals to mc square is the Einstein energy mass relation. Here mass is one atomic mass unit, and which is equals to how much? 1.66 into 10 power minus 27. So if you substitute these values in the energy mass relation, that is C and M values, you will get the value of energy, isn't it? Energy of that nucleus. So in electron volt you will find. So that is 1.66 into 10 power minus 27 into 3 into 10 power 8 whole square joule, isn't it? It is in joules. 1 electron volt is defined as the energy of an electron when it is accelerated through a potential of 1 volt. Okay. When it is accelerated, so it is defined. EV is defined as the energy of electron when it is accelerated through a potential difference of 1 volt. 1 volt to pass on to 1 volt, how much energy is needed? That is for electron. Here electron volt is equals to 1 electron volt is equals to 1.6 into 10 power minus 19 coulomb. Okay. Into volt, that is 1 volt. So 1 electron volt is equals to 1.6 into 10 power minus 19 coulomb volt. 1 electron volt, that is given by 1.66 into 10 power minus 19 joules. They have converted that coulomb volt into joules. Okay. So, so here we have found the energy of that uh, nucleus, that is calculated in electron volts. Okay. By using the Einstein energy mass relation. Okay. So here, if you see, here if you see, E is equal to, that is energy is equal to 1.66 into 10 power minus 27 into, that is, this is the uh, that is 1 AMU value, that is mass value, that is 1.6 into 10 power minus 27. This is C square, mc square, that is 3 into 10 power 18, 8 whole square, mc square by, this is 1 electron volt value. Sorry. 1 electron volt value, that is 1.6 into 10 power minus 19. That is, we have divided this C so that you will get in terms of electron volts, the value of the in electron volts. So 931 million electron volts. How much the energy? The energy will be 931 million electron volts, that is mega electron volt. Okay. So energy of the nucleus is how much? 931 mega electron volt. Thus, energy equivalent of 1 AMU. So, 1 AMU equivalent mass is energy is how much? That is 931 mega electron volt. Here, if you see the nuclear mass, so just now we have said what are the actually what does the nucleus contains? Nucleus contains protons and neutrons, isn't it? The nucleus contains protons and neutrons. Assumed nuclear mass is how, what then? Protons mass and neutrons mass, isn't it? So Z is here number of protons into mass of the proton. Okay. Plus this is number of neutrons, that is into mass of the neutrons. Here capital small mp and mn are the mass of a proton and a neutron. Okay. It is found that the mass of a stable nucleus is less than that of less than the total mass of the nucleus. So mass of the stable nucleus, if you consider, that will be less than that of the number of total mass of the nucleons. If you add protons and neutrons masses into number, that will be greater than that of the nucleus mass, because there will be some energy to find that. Okay, you will see that also. So if you combine all the masses of protons and neutrons, it will be more comparatively the nucleus mass. Are you understanding? So mass of a nucleus, that is small m, it is less than mass of the protons, mass of the neutrons here. Okay, number of protons into mass proton, number of neutrons into mass neutron. Okay, here ZMP is also ZMP is what? Number of protons into mass proton. This is also plus number of neutrons into mass neutrons minus capital M. Here delta M is the mass defect. So it is mass defect. Delta M is what? Change in mass is the mass defect. Mass of the nucleons to mass of the nucleus. Mass of the nucleons to individually mass of the nucleons to mass of the nucleus, that is delta M, mass defect, we will say. That's the difference in total mass of the nucleons and the actual mass of the nucleus. So total mass of the nucleons to actual mass of the nucleus is called what? Is called the mass defect. Okay. So it is a mass defect here. Here delta M is mass defect. It is given by ZMP, that is mass of the number of protons into mass of the proton, plus number of neutrons into mass of the neutrons, plus number of protons into mass of the electron, minus M, that is mass of hydrogen, plus this is hydrogen atom, protons, this is hydrogen atom, plus number of neutrons into mass of the neutrons, minus capital M. Capital M is a mass, okay, nucleus mass. So where MH represents mass of the hydrogen atom. So this is it. You have to remember that nucleus mass is what? Nucleus mass is nothing but protons and neutrons mass. But there will be some energy which binds the protons and neutrons. That energy is deflected in the nucleus mass to the nucleons mass actually. So that is called the mass defect here. So to go for other slide. So this is the binding energy. Just now I am discussing that it is the binding energy. So here binding energy is what? When protons and neutrons combine, when protons and neutrons combine to form a nucleus. So the mass disappears. In neutrons combine to form nucleus, the mass that disappears, mass defect, is converted into equal amount of energy. This energy is called the binding energy of the nucleus. So these protons and neutrons are, when they are added, when they are combined to form the nucleus, for combining of these nucleus, there must be some energy needed. The energy needed for the binding of these protons and neutrons, that energy is what? Binding energy. We call it as a binding energy of the nucleus, and the defect of mass of the protons, mass of the nucleons, that is protons mass and neutrons mass combined to, compared to nucleus mass, that mass is called the mass defect, which is disappearing. Okay, which is disappear, the mass that disappears. That this disappearing mass is converted as the energy. Okay, that is mc square. The mc square is what? Einstein's relation, right? Delta M is mc square. Delta M is a mass defect. Okay, is converted into, the defected mass is converted into energy. The energy, that energy is called binding energy, and it is given by binding energy B is equals to ZMP. Z is what? Number of protons into mass of the proton plus number of neutrons into mass of the neutron minus small m, that is mass, by into C square. That is delta MC square. Delta M is a mass defect, C square. It determines its stability against disintegration. So it determines, this determines that disintegration stability will be against the disintegration. As the mass is disintegrating, the stability is increasing. This is how it will be. If the binding energy is large, so if the binding energy is large, the nucleus will be more stable, isn't it? So it may lose some mass, but the binding, if the binding energy is more, the nucleus will be more stable here. So the binding energy per nucleon varies from element to element. The binding energy per nucleon varies from element to element. Okay. The binding energy for one element will be different and the other element will be different, because their stability is their valency is different. That uh, uh, binding means if you go for inert gases, their stability is more, isn't it? Their stability is more because the binding energy for their neutrons is more. So this is the graph of the binding energy. If you see, the binding energy for hydrogen is here, isotope. Hydrogen is here, and it is like this. Okay, the binding energy graph is helium is more, beryllium is more, carbon is more, like this. Okay, this the binding energy per neutron as a fraction of mass number is plotted in the figure. This is the binding energy graph. Okay, so explanation of this binding. So if you see the explanation of binding energy here, so the binding energy per nucleon, the binding energy per nucleon increases sharply with mass number A upon 20. So the binding energy per nucleons will be sharply increasing to 20. If you see the graph, so up to 20, from here to up to 20, the binding energy is increasing sharply, isn't it? Here, see, from hydrogen to helium, it has increased, like this, isn't it? From for 20 up to here, it has increased. After that, you see 56 is here and 127 is here. And it is again gradually decreasing. Let us see that. So, the binding energy per nucleon increases sharply with mass number A up to 20. It increases slowly after 20. So, after mass number 20, it is increasing slowly. For less than 20, for less than 20, there exists a recurrence of peaks corresponding to those nucleus. So there will be recurrence of peaks as as you observe, recurrence of peaks here. These are the peaks here. Recurrence of peaks we are observing, whose mass numbers are multiples of 4, and they contain not only equal but also even number of protons and neutrons. So which are having even number of protons. So you just see here 8 is a multiple of 4, 16 is a multiple of 4, isn't it? And here 12 is a multiple of 4, 8 is a multiple of 4, 4 is a multiple of 4, isn't it? So this gives the recurrence in their peaks, okay, whose mass numbers are multiples of 4. They contain not only equal but also even number of protons and neutrons. These will contain a even number of protons and neutrons. For example, if you see, these are the example here. Example, helium 24, beryllium 48, carbon 612, oxygen 816, neon 10, 20. The curve becomes almost flat for the mass numbers 40 and 120. Beyond 120, it decreases slower. Yes, it increases. If you see 40 and 120, 40 and 120, here 40 to 120, maybe it is here 40. Oh, here it is from here to here. The curve is so flat, isn't it? The curve is so flat. There is no much change in that curve. Beyond 120, it decreases slowly as A increases. After 120, what happens? It is decreasing gradually, isn't it? As the mass number is increasing, it is decreasing gradually. So as the number of nucleons increases in the nucleus, the binding energy between those nucleons is decreasing. As these are unstable, these elements are unstable, we don't see much mass numbers after this one. There will be disintegration of these nucleus, right? There will be disintegration of these nucleus. Due to the disintegration of these nucleus, there will be emission of these alpha, beta, and gamma rays happens, isn't it? Alpha rays, mainly of alpha decay we will observe as the uh, mass number increases and element atomic number increases. This is this is the reason, because there is no much atomic numbers more than 150, 160. Okay, you can observe, because they are unstable. The binding energy per nucleon the binding energy per nucleon reaches binding energy per nu- the binding energy per nucleon reaches a maximum of MeV at A is equals to 56. At iron nucleus, if you see, the binding energy per nucleus is reaches maximum. At here, the binding energy per nucleus is more, isn't it? It is the maximum peak point. From here, it is gradually decreasing as the mass number decreasing. So the binding energy per nucleon reaches a maximum of MeV at A is equals to, that is mass number is equals to 56, corresponding to the iron nucleus, that is 26 Fe 56. 56 is the mass number here, 26 is the atomic number is here. Hence, iron nucleus is more stable. So that's why the iron nucleus is most stable element here. Stable because it has binding energy per nucleon is more here. After this reach of this iron element, that there will be decrease, there will be fall, gradual fall in the binding energy, isn't it? The average binding energy per nucleon, the average binding energy per nucleon is about 8.5 mega electron volt per nuclei. So the average binding energy per nucleon is how much? Is about 8.5 mega electron volt per nuclei, having mass number ranging between 40 and 120. Okay, average binding energy is how much? 8.5 mega electron volt for ranging of mass numbers 40 and 120. These elements are comparatively more stable and non-radioactive. So these elements are what? Comparatively more stable and non-radioactive. For higher mass numbers, the curve drops slowly. So as I just now said, as the mass number increases, the curve will be dropping slowly, and the binding energy per nucleon is about 7.6 mega electron. The binding energy per nucleons, this one's for uranium is how much? 7.6 mega electrons. If you see for this one 40 to 120, it is 8.5. As it is, as the mass number is increasing, as the number of nucleons are increasing, there is increasing in binding energy, decreasing in binding energy. That is 7.6 mega electron. That's why there will be decay in this uranium. Hence, they are unstable and radioactive. This is why this uranium is unstable and radioactive, and it will decay as thorium and alpha particle, isn't it? So, the lesser amount of binding energy for lighter and heavier nuclei. Okay, the lesser amount of binding energy for lighter and heavier nuclei. Explain nuclear fusion and fusion and fission respectively. For lighter nuclei, it will be fusion. For the heavier nuclear, it will be fission. These will help to study this binding. Large amount of energy will be liberated if lighter nuclei are fused to form heavier one. Yeah, a lighter amount, large amount of energy will be liberated if lighter nuclei are fused to form heavier one. Okay, if so many number of light nuclei are combined to form a heavier one, there will be, then the energy loss will be so much. Okay, the energy released will be more. That is called fusion. Actually. Small element of nucleus are combined to form a large one, or if heavier nuclei are split into lighter ones, fission happens. Uranium, if you go for the example of uranium, if you see uranium here, uranium is large nuclei and it is splitting and it is giving a lighter ones. Okay, by process of fission. Okay, so you just see that there will be large peak where there will be large peak observed at iron nucleus, and the maximum that is more stable. The iron nucleus is more stable, and from 40 to 120 atomic mass, from 40 to 120 mass number, the average binding energy is how much? The average binding energy is 8.5. Again, if you go for uranium, which is having some more mass number, that is 7.6 mega electron volts. These nucleus, which are having higher mass number or higher atomic number, these will participate in fission, whereas for which is having large binding energy, which are in lighter, which are having lighter nuclei, those will combine to form fusion and heavier one. Okay. So next we are going to discuss about the nucleus models actually. Nucleus models we have to discuss. So let us see what are the nucleus models. So first one is, actually we have in our syllabus we have a shell model as well as a liquid drop model. We'll try to discuss liquid drop model in this class. In next class, we will try to discuss the shell model. So, the liquid drop model was first proposed by George Gamow and further developed by Niels Bohr and John Wheeler. So, these are the three scientists who have tried to propose this model and develop this model. So, first was proposed by Gamow, and next further this model is developed by Niels Bohr and John Wheeler. So there are some postulates of this liquid drop model. Means we are considering that nucleus as a liquid drop, and they try to explain the postulates by using this liquid drop. Nucleus is a homogeneous entity consisting of certain number of protons and neutrons. Nucleus is a homogeneous entity. Okay, it is what? A homogeneous entity consisting of certain number of protons and neutrons. According to this liquid drop model, this is having number of protons and neutrons, which is a homogeneous entity. Each nucleon interacts strongly with all its neighbors. So each nucleon will be interacting strongly with all its neighbors, means protons, neutrons. Nucleon means again these are protons and neutrons. They are strongly interacting with these neighbors. Consider the collective motion of all the nucleus. They are considering the collective motion of all the nucleus. The interaction force or nuclear force is assumed to be short range, one tending to saturation. So these are uh, these forces between these nucleons is assumed to be short range. Okay, short range forces. Thus, nuclear force is similar to that of intermolecular force of attraction in a liquid form. So as these are short range forces, these nuclear forces, we are considering this nuclear force, we are means we are giving the analogy of these nucleons to the attraction of a liquid drop. In a liquid drop, there will be intermolecular force. Okay, there will be intermolecular force between the liquids, uh, between the in a liquid. So that we are taking the analogy of the nucleons to the intermolecular force between the molecules. Okay, so nuclear force is independent of charge and spin of the nucleus. So nuclear force is what? Is independent of charge. Is independent of charge and spin of the nucleus. This doesn't depend on the charge and spin of nucleons. Okay. This nuclear force doesn't depend on charge and spin of the nucleus. Behavior of nucleus is comparable to that of a liquid drop. So behavior of nucleus. So as the nucleons are combined uh, by nuclear forces, that that nucleus is comparable to a liquid drop. Liquid drop, in the liquid drop, what happens? There will be intermolecular forces which which makes the liquid to be in a spherical shape, isn't it? So the intermolecular force of attraction between a liquid drop and nuclear forces between the nucleons. We are comparing these nuclear forces to the intermolecular forces. We are comparing nuclear forces to the intermolecular forces. Okay. Nuclear forces to the intermolecular forces. Okay. Thus, these are compared. These are the postulates. Next, if you go, let us see this one. Here, if you see, if the extra energy is large, oscillations may be so violent that stage C and ultimately stage D may approach. The nucleus is now dumbbell shaped, and both parts of the dumbbell which are not necessarily of equal size carry positive charge. The energy required to change the nucleus from stage A to stage D is called fission barrier. The nucleus is now in critical state because once this stage D reach the final fission into fragments, stage E is inevitable on account of repulsion between the fragments. Okay, here if you see, if the extra energy is large, so if the extra energy is large, what happens? It reaches to the D. Okay, sorry, extra energy is large. Oscillations may be so violent that stage C and ultimately stage D approach. So stage D means it will be like this. That is, both parts of dumbbell which are not necessarily equal size carry positive charge. The energy required to the nucleus from A to D is approached. So here if you see, so this is the stage A. If you consider, this is stage B, this is stage C, this is stage D. Okay, just consider these stages. So first neutron here, but is plus spherical, so it will be giving a spheroid. Okay, if you see, if the extra energy is large, oscillations may be so violent that stage C and ultimately stage D approach. So if the oscillations are more in the in the liquid, in the liquid, so what happens? There will be direct dumbbell shape. Dumbbell shape will be formed. Here, this is the shape it is formed. This is the shape it is formed. So it will be spilled out as a droplets actually. Okay. So these are both positively charged actually, which are not necessarily equal charge, carry positive charge. The they may be positive charge or not. The energy required to change the nucleus from stage A to stage D is called fission barrier. So the energy required to change from this stage to this stage is called what? Fission barrier. Okay, that is called fission barrier. The nucleus is now critical state. In what? The nucleus in the it is in the critical state because once stage D is reached, the final fission into fragments, stage E, is inevitable on account of repulsion between the fragments. So as this happens, as the stage D happens, it will be in a critical state, it will repel, right? It will be repelling. So let us see the advantages of liquid drop model. Let us see some advantages of liquid drop model. Where it provides basis for the equation of Weizsäcker for calculating the accurate binding energies of nuclei and their atomic masses. So, so it provides what? It provides a basic basis for the Weizsäcker semi-empirical formula. There will be an important question, that is semi-empirical formula will be there, that gives the energies of the nucleus. Okay, that gives the energies of the nucleus and binding energy and their atomic masses. So first advantage of liquid drop order is that it provides basis for the equation of Weizsäcker semi-empirical mass formula. Weizsäcker is a scientist for calculating binding. So here Weizsäcker is scientist. Okay. He given some equation. By this equation, we can find the energies, nuclear energies, atomic masses of the following that nucleons. Okay. So second advantage is radioactive decay could be predicted correctly. By using this, radioactive decay can also be predicted because as the nucleus becomes large, means size of the, if you go for example of liquid also, what happens if the size of the water drop is more, what happens? It will try to break into small droplets, isn't it? Because as that is big drop, what happens? The nuclear forces, the molecular interactive forces becomes less between those molecules and will die. They will try to split up. Okay, split up as droplets. In the case of the nucleus also, as the size of the nucleus is becoming more, there will be decreasing in the strong forces. There will be increasing in the Coulomb repulsive forces. There will be domination of Coulomb repulsive forces on the nuclear forces. That's why there will be radioactivity that can be studied by using this liquid drop model. So radioactive decay could be predicted by this model. Okay? It could explain nuclear fission reaction. Just now we have seen that this is also same. So as that of the example of sorry, radioactive decay, it could explain the nuclear fission reaction. Okay. It explains the mechanism of low energy nuclear reactions. It also explains the mechanism of low energy nuclear reactions. Okay. It explains it predicts A and B emission properties. So what happens? It predicts the A and B uh, emission properties. Okay. So actually what happens in the nucleus, we have strong nuclear forces. Okay. Strong nuclear forces That forces, the nuclear forces, are due to the Yukawa meson theory. There will be some theories on this nuclear forces, that is Yukawa meson theory. We will try to study tomorrow, but nuclear in the next class. I mean, nuclear stability also there. You will try to see how the nuclear stability will be there. Okay, it predicts A and B emission properties capable of explaining nuclear properties in excited state. So this liquid drop model is capable of explaining nuclear properties okay, in an excited state. So let us see the limitations. Limitation of liquid drop model. What are the drawbacks of this liquid drop model? Periodicity in a nuclear properties at magic numbers of protons and neutrons does not find any satisfactory explanation in this model. That is, fails to explain magic numbers. There are some numbers of numbers means mass number or number of protons or neutrons. In those numbers means proton having 8, number of protons are 8, number of protons are 12, number of protons which are 20. So there are numbers, what are magic numbers in the next coming classes we will try to study. In those numbers of atomic mass or uh, that is atomic number, where the stability of that nucleus is very much high. Why this stability is occurring? This model couldn't explain that. Okay, this model couldn't explain that magic numbers. Okay, the magic numbers aren't explained by this liquid drop model. Okay, this is one failure. It fails to explain the stability of heavy nucleus. So heavy nucleus stability also it was couldn't explained. It couldn't explain the stability of heavy nucleus. This model is not consistent with the proton-proton and neutron pairing effects. So it is not consistent with proton-proton and neutron pairing effects, which are prominently observed in stable nuclei. So these in a stable nuclei, there will be consistency of proton and proton and neutron pairings will be there. So that couldn't explained by this liquid drop model. The model ignores independent motions of nucleons, magnetic moment effects. So this model ignores the independent motions of nucleons, magnetic moments. Okay. So this is the liquid drop model. We have shell model also, and we have some theories, Yukawa meson theory, and also some nuclear stability graphs. We'll try to discuss those graphs actually. So if you go for nuclear models, there are three models actually. First, there is Fermi model also will be there. But we are in the syllabus we have only shell model and this liquid drop model. We'll try to discuss these models. So as a just we'll go through the summary ones. What is the radius? How the radius is found? The radius is found that it is found by the formula R directly proportional to A by 3, isn't it? Go for summary of the today's lecture. To go here, if you see the nucleus size was found find out by the formula R directly proportional to A power 1 by 3. R naught is the proportionality constant here. It is equals to 1 by 3 F, that is Fermi. Fermi is equals to 10 power minus 15 meters. Okay. So nucleus density, as we know, density formula is mass per volume. We will try to find the nuclear density by nuclear mass by nuclear volume. Nuclear mass is A into capital Mn, mass of the nucleons to atomic mass. So we will multiply these two by divide by nuclear volume, that is 4 by 3 pi r cube, that is volume of the sphere, right? Sphere, 4 by 3 pi r. So we will divide this one. We know the mass of the neutron, and we'll try to calculate by using nuclear density. Okay. Nuclear charge, you have to remember the nuclear charge, that is 1.6 into 10 power minus 19 coulomb. Okay. 1.66 into 10 power minus 19 coulomb. And nuclear charge is given by ZD. How it is given? Given by ZD. Atomic mass unit. Atomic mass unit is equal. So atomic mass unit is nothing but 1/12 of the carbon element. Okay. Carbon atom mass, 1/12 of the carbon. So it is given by 1.66 into 10 power minus 27 kg. The mass of a proton MP is equals to 1.007276 AU. The mass of the neutron is Mn is equals to 1.008665 AU. So this is the energy equivalence relation. From this, we will try to find the energy of the nucleus. E is equals to mc square. We know the m is equals to 1 atomic mass unit, and c is the velocity of the light. Velocity of the light, you will substitute, and you will get the energy relation. Okay, energy value, that is 931 mega electron volts. How much? Energy of the nucleus is 931 mega electron volt. And next, we have gone through the nuclear mass also. Nuclear mass is nothing but mass of the protons plus mass of the neutrons, but the mass of the nucleus is less than the mass of the protons and neutrons combined. Okay, nucleon's mass is more comparatively mass of the nucleus, because when we combine the nucleus mass, there will be energy needed or released. Due to that energy, there will be defect in the mass. There will be defect in the mass. So that mass is called the mass defect, and there will be, that is converted. The mass is converted into energy by energy, and it is given by delta mc square. The next slides we will see. Okay. So this is the binding energy. Just now, as I said, there will be release in the energy. There will be release in the energy due to the combination of combining of the protons and neutrons. That combining of protons and neutrons gives combining of protons and neutrons decreases the mass, decreasing the mass of the nucleus, nucleons to the mass of the nucleus. That is given by mass defect, and it is equivalent to F delta mc square, which is called binding energy of the nucleus. Okay. So that is given by this equation. Remember this equation, this is important. Zmp plus Zmn minus small m c square, which is equals to, this is mass of the nucleus actually. Capital M is this, M is what? Mass of the nucleus. This is number of protons to mass of the protons, number of neutrons into mass of the neutrons. So delta mc square. This is what? Delta M. There is change in mass to the nucleus to the neutrons. Okay. It is delta mc square. So it gives the stability of the against the disintegration. Binding energy gives the stability against disintegration. Binding energy, when the binding energy is large, nucleus is stable. Okay. Binding energy per neutron is given like this. Up to, this is the maximum binding energy we will find in the iron. That is atomic number 6, mass number 56. Okay. It will be sharply increased to 20, and there will be fluctuations in between this 2 to 20. Mass number 4 to 20, there will be fluctuations. Okay. After that, that is iron, what happens? Ferrous, what happens? There will be slowly gradual decrease in the binding energy. There will be gradual decrease in the binding energy. Okay. So nucleons increase sharply with mass number A up to 20. Okay. Decreases slowly after 20. Okay. Decreases slowly after 20 and decreases slowly after 56. So this helium, these are the examples we are seeing, and this is We have seen up to 40 to 20, the binding energy per nucleon is 8.5 mega electron volts. For uranium, it is 7.6 mega electron volts. As the size of the nucleus increases, the binding energy decreases. Okay, binding energy decreases means what? There will be disintegration of the nucleus. Okay, there will be disintegration. There is a possibility of disintegration of the nucleus. Okay, so as a nucleus is large, what happens? There may be fusion. Fusion occurs into lighter ones. If the nucleus is small, which is having so much binding energy, and they'll try to combine and try to form a fusion. Okay. So liquid drop model, we have compared liquid drop with the uh, nucleus. Nucleus contains protons and neutrons. There will be nuclear forces between these protons and neutrons. When we compare this liquid drop, their molecules, there will be intermolecular force between the uh, drops, okay, water molecules. And it is homogeneous entity consisting of protons and neutrons. Which nuclear contains, we have discussed this collective motion. Okay. So we have seen that liquid drop can explain the phenomenon of nuclear fission. The liquid drop has spherical shape due to intermolecular forces responsible for the surface tension. So, due to the surface tension, liquid drop will be in a spherical, okay, spherical shape. On applying large external force, the sphere may change into ellipsoid. So, when we apply the force on the sphere, it will change to ellipsoid. If the external force is sufficiently large, ellipsoid may change into dumbbell shape. Again, if you apply the force, what happens? Ellipsoid will change into a dumbbell shape, and may even break at narrow ways into two portions, so that it will break into two portions uh, after some minutes. So, firstly, the liquid drop is the fusion of the nucleus is explained comparatively to the liquid drop. Actually, liquid drop is comparing the fusion of the nucleus. As a nucleus size increases, it will fission out and it will be make it made into lighter ones, isn't it? In that way, liquid drop, when it is spherical in shape, it so spherical in shape, the responsible is for the by the surface tension. Surface tension make it push spherical phase, but if you apply the force externally, that will change into spherical shape, change to ellipsoid, and ellipsoid change to dumbbell shape, and dumbbell shape will break down after some energy into two portions. Okay, according to Wheeler theory, the nucleus behaves like a liquid drop. So, Bohr-Wheeler theory, uh, accordingly, the nucleus will behave like a liquid drop. The nucleus captures a neutron falling on it, forms a compound nucleus, which is highly energetic. The extra energy may set up series of rapid oscillations in the spherical compound nucleus, as labeled as a figure below. As a result of these oscillations, the shape of the nucleus may change at the time form. So it happens. We have discussed earlier that spherical shape is made to made ellipsoid, ellipsoid to dumbbell, dumbbell to it is breaking as parts. Okay. So this is compared to fission reaction. When neutron is spherical in shape, so nucleus uh, ellipsoid shape, ellipsoid to dumbbell shape, and it is breaking as two parts. Okay, these are the some advantages of liquid drop model. And these are the limitations of drop. The next class we will try to study the semi-empirical mass formula, which is given by Wiesecker, and shell model. These are very important models. Shell model also we will discuss. This is one model. Liquid drop, we are comparing nucleus with the liquid drop ones, and we are comparing uh, shell with the shell ones. Okay, try to discuss the next class. So this is for today. Thank you.